Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And very good morning, everyone. So let's start the class with the Kitab, Al-Fatiha, and the prayers. Bismillah. Okay, can everyone hear my voice clearly? Okay, just to make sure that, okay, good. Okay, yeah, I see some. Yeah, thank you. Okay, so for those who attend this lecture with your friends, okay, maybe okay, please do it right now, and please get the proper way um, to make sure that sorry. Okay, all right. So let's start the class with this topic. Hopefully, all of you have already downloaded the notes I have given to your class rep last night. Okay, so you can download it and you can do whatever you want to the notes. Okay, but please make sure um, to 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 at least give some credits. Okay, at least you can share with your friends. Yeah, I don't mind, but please get a proper way. When I explain something, please make sure you do understand. And if you don't understand, just uh, ask me later, maybe in our physical class, or maybe you can type it here. Okay, regardless of whatever you want, but you can ask me anytime. All right. So the topic is rotational motion. So let me present the slide. Okay. So this is the topic. Okay, rotational equilibrium and dynamics. Okay, I believe that all of you have already discussed or have already go through all the topics regarding rotational motion. Okay, the rotational motion, that the topic you learn uh, before midterm test and before your break. So this is the topic, which is this topic falls in the chapter 8 in your textbook. Okay, so this is the topic for the chapter 8. Okay, so first of all, my name is Fuzairi. Okay, I will conduct your lecture from this time being. All right. So these are the learning outcomes for the topic. Okay. So at the end of the chapter, the student should be able to define torque. Okay. So to define torque, to apply, sorry, okay, to apply the definitions of torque on object undergoing rotational dynamics, state the two conditions. So, a moment. Kenapa dia macam tu? Okay. So state the two conditions of the mechanical equilibrium. What does it mean by the mechanical equilibrium? To apply the conditions of equilibrium. Okay, what does it mean by the mechanical equilibrium and the conditions, of course? And to define the center of gravity, this is the topic. This is the subtopic that we learn it doesn't involve any calculations. When we talk about center of gravity or center of mass, okay, we only learn is as a qualitative way. Okay, as you know, the qualitative did not use any calculations, but at least you need to know if the question can be asked to you, okay, during your final, okay, because from this time on, okay, all the topics that we discuss afterwards, we discuss from this chapter, at least from the chapter 5 and beyond, it should be falls into the final. Okay, so define the center of gravity and define the center of mass. Yeah, falls under qualitative methods. Okay, that means it doesn't involve any calculations. And then you need to apply the conditions of mechanical equilibrium, the angular momentum, and if which is in the angular momentum, you need to define the moment of inertia. Okay, this is not the inertia that you learned in chapter 1. Sorry, you learned in chapter Newton's law. Okay, which is chapter 4. Okay, but this one is the moment of inertia. Okay, and in the angular momentum, you also need to learn about to apply the moment of inertia to the various object. Okay, that means the subtopic of moment inertia involved in the how you can do or what is the moment of inertia for the several objects, various objects. Okay, it did not have the same moment. Okay, each category or each objects, yeah, of course, it can be made into different shapes. So therefore, the moment of the inertia should be different. Okay, and we also need to learn about rotational second law of the physical system, which is the torque equals to I alpha. Torque equals to I alpha. Torque equals to I alpha. Okay, right. So today we want to focus on torque. Okay, we want to focus on torque, or should I say, in rotational motion. Okay, in rotational motion, you have established. Okay, may I call that as you have established or you do understand about theta. Okay, theta, that means rotational position or position, angular position. We call that as angular position. And how about omega? This is the angular velocity or angular speed. And then we have alpha, which is angular acceleration. Right? Now you have three different terms we learn about in rotational motion that we can define it here. Okay, so what is torque actually? Okay, so this is okay, when we look at the torque, okay, it's actually you have experienced it in your daily life. Okay, so let's look at the bird's eye view of the door, which we okay, bird's eye view, that means daripada atas, pandangan atas of door, that means pintu. Okay, now you have hinge, okay, ataupun engsel dia tu dekat hujung, dan you have a knob ataupun dia punya tombol pintu. Okay, so this is actually a door in the bird's eye view. Okay, so at this particular door, okay, you may see there is a R with the arrow, with the slight arrow, and you have F. So normally when you look to F, you know this is a force. That means the applied force. And of course, R is something that related to a arm, or should I say, sometimes you can call it as vector position. Okay, vector position. That means it's a position, but it's a vector. Okay, so as you can, if Dr. Aida have mentioned in chapter 1 about how we multiply vectors. Okay, so in the multiplications of vectors, you can be divided into two. Okay, I want to emphasize on this part: multiplication of vector. Okay, can be divided into dot product, and also cross product. Okay, and how you multiply the vector. For example, you have two vectors. Here you have two vectors, vector A and vector B, and you want to multiply it. Okay, you want to darab dia. Vector A kali dengan vector B. Then you have two ways to multiply it. Number one is using a dot product, and number two is using a cross product. So you have learned about dot product. Remember, when you learn about work is equivalent to F dot D. Okay, this is a dot product, because force dot displacement. Okay, force is a vector quantity and displacement is also vector quantity, but we multiply it using dot product. That means for the dot product, we can have a scalar quantity. Am I right? Because work falls under scalar quantity. It doesn't involve any directions. Okay, because scalar quantity is a magnitude without directions. Okay, now you look into a cross product. Okay, in cross product, there is also involve vectors of vector multiplication. For example, we multiply vector A crossing a vector B, so you can have a number one. Okay, is either scalar quantity, and also you may have a vector quantity. So mostly is here. Okay, for instance, when we multiply a vector using cross product, that means using a multiplication using cross product. So if A cross B, okay, the answer should be A cross B. Okay, normal multiplication. That means if the two vectors, vector A and vector B, right, multiply using cross product, we can obtain a vector quantity. So this is a vector quantity. Okay, it's because the answer is similar to the question, because the question involves a vector. How do I know a vector? Because we have A and B with the arrow. A and B is arrow is the indication of that A is a vector and B is also a vector. Okay, so when you multiply A and B, okay, it's either you can have a vector quantity like this one, and maybe if A, vector A cross vector B, and then you put a modulus, then you may get A, B, sine theta. And that means you can have a magnitude here. So, in order to find the magnitude of the vector cross product, so you can put a modulus there, okay, and then we can have a magnitude. And so that's why, okay, of course, a cross product examples of cross product is a torque. So today we will learn about torque. That means you multiply the vectors using cross product. Okay, so you multiply the vector. That means you multiply R. Okay, in this case, you multiply R and F. Okay, because both considered to have a vector, because considered to be a vector, because force you already know this force is a vector, but position, okay, length. This length is not as ordinary length. Of course, somewhere in the chapter, it can also be noted as a lever arm. Okay, lever arm. But mostly when you look at R, is actually a vector position. So you should know that R is a vector. That means R considered to have a directions. And mostly R is what? R is the displacement, is the position of the force to the center of rotation. So the hinge or axle yang ada pada pintu, we thought is to be axis of rotation. So from this simple figure, okay, we will know that this door or this product, this item, is actually can move because of we apply some forces towards this axis of rotation. While at the same time, we may have a vector position. We may have some length, and when we apply to a certain movement, so you apply a force is maybe that way, okay, to the upward position or to the downward position. And then, of course, with the proper axis of rotation, you may have a torque. Okay, so in other words, now you can see, okay, so, right, so you already know that forces cause some acceleration. So that's torque. Okay, when you look into torque, okay, with the symbol torque, tau. Okay, this is a tau in in a Greek consonant. The torque cause and some angular acceleration. Okay, that means torque uh, can produce some alpha angular acceleration. Okay, you look at the figure back, okay, which is here. So can you imagine the door is free to rotate? And how is possible this door is rotating? Okay, if you can imagine right now, okay, the door will be based on the axis of rotation. The hinge should act as the axis of rotation. How do I know it's axis of rotation? Because if you try to imagine, let's say, okay, look at my pen here. Okay, if this one happen to be your hinge, okay, this one is your hinge. Sorry. Okay, and when I move some force towards upward here, okay, so and then of course this one will rotate at a certain theta. Okay, so that's why when I say that the force can cause some angular acceleration, is due because of we put the hinge over here, and then, okay, because this one is already fixed, okay, it's either you pull it upward or you pull it downward, it can cause you a certain angular. So in this case, it produces some angular acceleration. There are three different factors, okay, that can determine the effectiveness of the door. So it's either number one, the magnitude of the force. Of course, when the um, when the people, okay, tend to open the door, okay, open the door with the different magnitude. Maybe your sister or your little brother try to open the door. Okay, the force is not going to be the same with your force. Sorry. Okay, of course, your force should be bigger compared to your sisters or your little sisters or your little brother's force. Okay, and then the position of the applications of the force. Okay, can you imagine the position of the application of the force? That means if we can consider, we can imagine if we pull it force in the upward position at the very end of the door, that means at the doorknob, or you maybe want to open the door, but you pull somewhere here. Can you imagine the difference? Yes, of course, the door should be rotating, okay, easily when it is moving very far compared to very far away from the axis of rotation. Okay, and then you look at the third factors, which is the angle at which is applied. Of course, we can consider at this kind of situation here. Sorry, well, in this force will have some right angle to the vector position. Okay, the theta is 90 degrees. And try to imagine that if we pull the door, instead of we push the door or we try to pull or push open the door in the right angle to the door, but instead of pulling or pushing at the right angle, we try to pull it here. Okay, that means the angle now have become, okay, parallel. Okay, when angle is parallel, that means here theta is 90, but right now your theta is 0. What will happen to the torque? Well, what will happen to the rotations of the using the force? These are the three situation that you should consider when you want to apply the torque. So the magnitude and the position of the force. Okay, that means or the position of the force can be noted as the position or the length of the vector position. Okay, the length of vector position. That means if we can consider F here, okay, in the very mid at the middle of the door, or maybe at the very end of the door, so the rotational motion should be different. Okay. So in general, a larger radial distance, okay, between the applied force and the axis of rotations results in a larger angular acceleration. So it's actually easy, okay, compared to the one that contain a smaller radial distance. Smaller r, okay, r that means, yeah, the length between force and the hinge, right? So if we apply some larger distance, so the larger the distance, uh, the angular acceleration should be increased. That means it's easy to rotate the door. Okay? Any question so far? If you have a question that you can ask me, okay? You can open, okay? Switch on the mic, or you may want to type it. Okay, no problem. Okay, good. Now we move to this part. Okay, so now you can see, okay, the radial distance will play an important role when you discussing about torque. Okay, how do I know that? How try to imagine these three figures. Okay, now this is a wrench, or something related to a wrench. Yeah. Okay, this is a wrench, and is it the function of the wrench to tighten the nuts of the okay, to tighten the nuts. So we should apply some forces to the wrench in order to tie or to loose up the nuts. Okay, screw nuts tu ya, ada the nuts kat sini. Can see here. Okay, now there are three different situations of the wrench. Okay, now you can see, and let's say this one is your position A, position B, and also position C. Okay, the position A, the force is actually at the very end and very close to the axis of rotation. How do I know this is the nuts or the head of the wrench is the axis of rotation? Because that is the where the wrench, okay, happen to be the one that make the wrench rotate. Okay, so these are the center of rotation at the very end, which is the here axis of rotation. Okay, this is also the axis of rotation because that is where you rotate the thing. So we are by using a wrench, so you can see the force, okay, in the figure A compared to figure C. Figure C have a very larger which figure C, okay, contain largest radial displacement or largest radial position but compared to figure A and also figure B. Okay. I'm sorry. When the force is applied farther out along the range, the magnitude of the torque, okay, you look here, the magnitude of the torque increases. Okay, that means the torque is perpendicular to the plane. Of course, the torque is perpendicular to the plane. The point O is usually chosen to coincide with the axis of object is rotating around, for example, edge of the door or hub of a merry-go-round. Okay, of course, other choices are possible. So you may see at a very specific Examples, okay, the axis of rotation are not the same. So maybe at the door, okay, like this one, okay, we can see that the hinge play important as a axis of rotation. Okay, but in this kind of wrench and nuts, okay, the nuts have become the axis of rotation to the situation. That means, okay, when the force is applied, okay, farther out, that means this one very the length is the largest one compared to A, part C. Okay, so the magnitude of the torque will also increase. Okay, we consider only forces acting in the plane perpendicular to the axis of rotation. So, for example, we don't include a force with the upward component on the merry-go-round railing, which can affect the merry-go-round's rotation. Under this condition, an object can rotate around the chosen axis in one or two directions. So that means is this one, okay, when we considering the torque, okay, we should always assume that, okay, it can move in only one plane. Plane, that means, that's, for example, in this case, okay, the wrench and the nuts have been put on the table, okay, di atas meja. So the plane is only in X and Y axis. Okay, the plane tu latar dia is only in the X and Y. This is X and this is Y axis. So plane tu duduk pada X and Y axis. It doesn't involve Z. Okay, that means the rotation, okay, you need to know the rotates, how to rotate in X, Y plane. So we put the axis of rotation in Z axis. Okay, so that means the wrench is not rotating about a Z axis or a Y X axis, no. Okay, it's rotating in the X and Y plane only. Okay, then we need to assume that, because when if we cannot assume that, then you may have some big problems involving torque. Okay, so now that is in terms of the distance of position vectors. Okay, so by convention, now you need to know, of course, the force is not only can be happen in that upward position, it can also took place in the downward position. Or in this case, okay, we may say, or you can imagine that, okay, when you apply to a certain things, okay, for instance, this one, right? You have, so when you put it, okay, to the forward position, so it can make this one, okay, it can make the rotation become a counterclockwise. And if you pull downward, this one, okay, it can make a clockwise position. So a convention, as a physicist, we need to make sure that um, in conventionally, the counterclockwise, okay, should give you a positive value, and the clockwise will give you a negative value. Okay, so counterclockwise will give you positive value, while at the same time the clockwise position will give you negative torque. Okay, what positive, negative? Torque. Positive, torque, negative. So when the force causes the object to rotate clockwise, the torque on the object is negative. So I have mentioned to you, okay, the clockwise or the counterclockwise will be based on our force at the axis of rotation. So you should know when you apply some force towards some axis. Okay, so you can have, or you can see that the situation should be counter or clockwise. Okay, so when two or more forces torques acts on an object, okay, at rest, the torques are added. Okay, if the net torque is a zero, the object starts rotating at an increasing rate. Okay, at an increasing rate. If the net torque is zero, the object's rates of rotation doesn't change. Okay, this condition should seem familiar to you from Newton's first law. Okay, well, in fact, we have a rotational analog to the first law that says that the rate of rotation of an object doesn't change unless the object is acted on by a net force, a net torque, sorry. So when two or more torques acts on an object, that means we need to find the net force. The net force, of course, when two or more forces involved in the conditions of a certain torque or a certain situation, so you need to apply, you need to form, you need to find of all because when you have R and force, so you may find a torque. So when there is another force, let's say pulling in this way, so there is a R and also F. So you need to apply a new torque. Okay, torque number one, torque number two. And if there is another force, yes, okay, that is torque number three. Because every forces possible in the situation should be counted. So should be found, should be calculated as a torque. Same goes to when we apply in work. Because when we have work, okay, for example, we have gravity. Gravity is a gravitational force. So you can find Fg. Okay, so in work, we need to find work for gravity. Okay, for example, when we have a normal force, so we need to find the work in the for the normal Wn. So same goes to this topic. Okay, so you need to address, you need to find the torque for each forces. Whenever you have force, so you need to find its torque, and of course, the net force or the net torque is based on the submission of delta torque. Okay. Okay, now look at these examples. So the torque can be measured or can be said as RF. Okay, R multiplied by F or R vector R, okay, cross vector F, RF. And the unit, SI unit will be Newton meter. Okay, because F Newton and R is in meter. But remember, this is the torque we are talking now. So torque can be measured or can be noted as RF sine theta. Same goes to when we multiply A, the one that I did in the first place. Okay, when you multiply using cross product, but you have a when you want to find the you want to find the magnitude, so you get it with the A, B sine theta. Okay, that means vector A crossing vector B with the proper modulus. That means we want to find the magnitude. So it's just not about the directions only, but we can measure a magnitude together. Okay, now let's look into several cases here. Okay, for instance, we have figure A. Okay, figure A. Then there is a hinge at the very end, very left end of your figure. And then you have some R. I think A, B, C contain the same R. But right now, you should focus on the force. That means force as it is. Okay, so look at the figure A. Figure A is when we apply a force to the doorknob. But in the conditions of the force and the vector position are parallel to it, parallel to each other. Therefore, here, okay, we are saying that this theta is equivalent to 0. And what happened when theta equals to 0? Okay, you can measure, you can put it theta 0, you put it inside this equation. So can you imagine RF sine theta, when sine 0, definitely the torque should be 0. Okay, emphasize back, sine 0 equals to 0. So regardless of the value r or f, so the torque should be 0. You cannot have a torque, you cannot move, you cannot make the door rotates, either clockwise or counterclockwise, because you are pulling the force, you are using the force, but in a very weird way. Should I say weird way? Kita tak buka pintu dengan tarik macam tu. Kita tak buat pintu terbuka atau tertutup. Okay, in fact, okay, we just use theta equals to 0. Okay, so that is also the same when you apply the force eh, for 180 degree. So what can you imagine where is 180 degree? So the R is here and the F is the same direction, not the same direction, but the opposite directions. That means theta equals to 180 degree. So for theta 180 degree, you put inside the equation, the top should be z, also 0. That means sine 0 and sine 180 degree, the top is z, 0. Okay, so therefore, you can imagine that when the sine, okay, when I try to imagine this one, okay, 0, 90, 180, 270, and this one is 360. So 0, 360, 180, all value of the theta will give you 0 torque. And at the same time, when torque equals to 90, torque equals to 270 will give you maximum value. Okay, so the difference between 90 and 270 is just a matter of positive and negative. So therefore, we can understand this one, right? When you look this several situation, we will understand that when you apply R multiply with F, or R you cross product with F, you should know the F that we are talking now is the F that is perpendicular to the R. Okay, the same things when you multiply or you do work. For instance, we multiply F dot D. But in fact, the real equation should be F D cos theta. That means when you rearrange, it's actually D F cos theta. That means the component of F that is parallel to the displacement. So therefore, uh, the theta should, if you want to find the maximum work, okay, the theta should be 0 or 180, because cos 0 will give you 1. Cos 180 degree will give you negative 1. Okay, but when you put it, yeah, uh, perpendicular to the displacement, what happened? So when theta equals to 90, cos 90 equals to 0. Cos 270 also equals to 0. So the torque and the work should be, okay, slightly inverse with each other. Okay, vice versa. Because in work, okay, our mentality is we want to find the component of work that is parallel to the displacement. But in torque, okay, we should find the work that is perpendicular to the displacement, because when perpendicular, sine 90 equals to 1. Sine 270 equals to negative 1, for instance. Okay, therefore, you may find the maximum torque. So, right now, I have mentioned about 0, 90, 180, 270, and also 360 degree. But what about other angle? Yes, therefore, there is a equation involve torque that is R F sine theta. Then you can put it any value that equivalent to sine theta. So, for instance, like this one, okay? Let's look at this situation. So you may have some axis of rotation over here, and you have some lever arm or the vector position, and you have force that is 30 degree in the from the y-axis, 30 degree from the y-axis. So how do I put that f sine theta? That means the component of f that is parallel to the r. Okay, parallel to the r. So how do I know that? Okay, now you can put it like this one and this one. So right now we put it f cos 30, and this one is f sine 30. So if we pick this one, f cos 30, okay, we bring that component and times with the r, okay, we may have a zero torque. But if you want to find the maximum torque, that is f sine 30 times with r. Because for f sine 30, the value is this component, okay, I put it here, blue color. This component is perpendicular to the vector position. So that's why we choose f sine theta. Okay, so this is another way of calculating a torque. Okay, so another way to understand this one is using what we call as lever arm. Okay, what is lever arm? Right. So a second way of understanding a sine theta, okay, as mentioned, okay, we actually have established that. Okay, this one, okay, this is f sine theta, and this one is f cos theta. Okay, so it's very easy to understand that one. But right now is we choose another type of ways to find d, because if there is a situation, some situation will be given without using any r. Okay, that means they have give you some lever arm, which is the sine theta factor to associate with the magnitude r of the position vector r. The quantity d will be equivalent to r sine theta. Okay, r sine theta, that means sine theta is equivalent to d over r. Okay, sine theta is equivalent to d times r. D over r, sorry. And then we multiply, d is equivalent to r sine theta. Okay, the value of torque depends on the chosen axis of rotation. So now you need to know, okay, in order to calculate torque, you need to find where is the center of rotation. Number one, to find the center of rotation. Number two is to determine the position vector. And then you need to know which forces involved in every situations. Okay. So right now, okay, we go straight away to these examples. Okay. The two disgruntled business people are trying to use a revolving door. Okay, normally, okay, when you are at the very situation of the revolving door. Can anyone imagine the revolving door, pintu yang berpusing? We hardly need to see in Malaysia, kita tak banyak pakai. Because the hinge is at the middle here. Hinge duduk di tengah. So that means when you want people go to this way, he wants to push the door so that the door will open towards that way. And at the same time, if one people wants to go out, he will be here, and then the door will move here. So that is called what we call as revolving doors. For those who doesn't understand that, you can Google or you can uh, uh, always use the YouTube to understand that. Okay, so the woman on the left exerts a force of 625 Newton, which is perpendicular to the door and 1.2 meters from the hub's centers. Okay, while the man on the right exerts a 850 newtons perpendicular to the door and 0.8 meters from the hub center. Fine. Fine, that means calculate the net torque on the revolving doors. Okay, so how to get the value? So you need to find each torque. So that means net torque will be based on torque number one plus torque number two. Doesn't matter what, the regardless of negative or positive. Okay, but net torque is actually the net on how we add all the torques involved in the situation. So in this case, we need to find the torque number one. Okay, look at how they represent that. Okay, so the torque number one, F is going upward. And look at where is the axis of rotation. Is on your right. Okay, on your right. So how to know that this torque is actually clockwise or counterclockwise? First of all, you need to determine that. Because force you can multiply R times S, and regardless of the theta, because all forces in this question is already perpendicular. That means sine 90. Sine 90. Okay, sine 90 is sine 90 equals to 1. So R times F, but how do we get negative? The negative will be based on what? Okay, so you take your pen and you put it on you put your the very end of your pen or your pencil at the axis of rotation. Okay, and you make sure you lock your fingers there. Okay, make sure you put the fingers, the pencils over here. Okay, you should lock here. Okay, lockkan jari awak di situ, and then of course the force is going up, and then you pull this your pencil towards up, then you can see that it move. Okay, the rotation should be clockwise. And then remember, when the rotation is clockwise, the value should be negative. And then the same goes happen to the force number two. When you have R and you have F2, so that means you can multiply to get torque number two. This one is torque number one. Okay. And then of course torque number two doesn't have positive and negative because it is a going that way counterclockwise. Counterclockwise positive value, clockwise negative value. Okay, when you add both the torque, then you may find that it is the net torque should be negative 70 Newton. And of course, when you look at the negative, you should know that the net torque should be clockwise position. Okay, you have a counterclockwise and you have a clockwise. Siapa yang lagi menang? Tengok the end of final answers with a negative. That means the net torque should be clockwise. Okay, look at the unit, right? Newton meters. Okay, so if there is question, I will stop here, and then we will continue back our lessons tomorrow, insyaAllah. Ada soalan tak?
Mana Priska?